Hello, everyone, and welcome to the Intermountain West Drought Early Warning System Drought Conditions and Outlooks Briefing. My name is Gretel Fallingstad, and I work with the National Integrated Drought Information System, or NIDIS, and manage the Intermountain West Drought Early Warning System. These bi-monthly drought briefings are in partnership with all 5 states in the Intermountain West region, which includes Arizona, New Mexico, Colorado, Utah, and Wyoming. We aim to provide the most up-to-date drought and climate information and connect climate service providers, resource managers, and build drought resilience across the nation. I wanted to give a shout out for a product that NIDIS produces in winter months. It's our snow drought updates, and our February 2025 snow drought update drops tomorrow. You can access that through that QR code or the link that you see there on the slide. As many of you know, snowpack typically acts as a natural reservoir, providing water throughout the drier summer months. And the lack of snowpack storage or the shift of snowmelt from that reservoir can be a challenge for water management and drought planning. We hope that you will engage with our snow drought products. We currently have been degrading across the Intermountain West in terms of drought. Arizona in the last couple of months went from 56.4% to 83.7% of the state in drought, with D3 expanding from 11.2% to 21.2%. Colorado degraded from 10.4% drought to 17.1% drought. New Mexico went from 29% to 36% with 5.4% in D3 or above. Utah degraded from 18.9 to 40.5%. And Wyoming was our only state that actually saw some improvements, though it has been suffering from drought for quite a few months. Went from 96.3 to 83.2. And we will hear more about those conditions from Tony Bergantino. And with that, I will introduce our 2 speakers for today. We will hear about our drought conditions across the entire Intermountain West region from Tony Bergantino. He is the director of the Wyoming State Climate Office and Water Resources Data System, where he has worked for over 30 years. In addition to drought, 2 very related research interests of his are snow hydrology and the consumptive use of water. After that, we'll hear from Dr. Jeffrey Deems, who has helped pioneer the use of LIDAR snow depth mapping in support of hydrologic science, water management, and avalanche mitigation. As a founding member of the NASA JPL Airborne Snow Observatory Science Team, he helped develop the LIDAR mapping and data fusion workflows while fostering connections with hydraulic forecasting and management entities. His interests and expertise in avalanche and snow hydrology research combine field data collection, modeling, and remote sensing in mid-latitude mountain locations in the western U.S. and around the globe, and actively further connections between science and management applications. I want to make sure our audience knows that you can put questions in the questions box within your GoToWebinar platform, and we will happily address those questions after we hear from our presenters. So without further ado, I will stop sharing and let Tony take over.
All right.
Looking good.
All right. Well, thanks for that intro, Gretel. And as Gretel said, I'm Tony Bergantino, Director of the Wyoming State Climate Office and the Water Resources Data System. We're a part of the Department of Atmospheric Science here at the University of Wyoming, and we're funded by the Wyoming Water Development Commission, with whom we work very closely as their technical arm. We compile GIS from their projects, assist consultants, develop standards, and so on. We also serve the state as a source for water and climate data, develop drought monitoring products, and we work with various agencies serving their hydrological and climatological needs. So let's just start out with some temperature and precipitation rankings for calendar year 2024. And these maps show how each state ranked compared to its own history over the last 130 years in terms of how warm or cold it was and how wet or dry it was compared to its history. On the left is the temperature, and every state is ranked in the warmer years throughout the country. And that ranking here is where 2024's temperature fell for each state compared to each annual temperature from 1895 through to 2024. In the Intermountain West, the states ranked as the second through the fourth warmest. Precipitation was a lot more mixed both across the country and in the Intermountain West. They're on the right side, with states like Wyoming and Arizona being on the dry side, Colorado being on the wetter side, and Utah being sort of in that normal band. So going to just looking at the water year 2025, which started in October and goes through, December of 2024 for this map, since the January data were not available. Temperatures here on the left were above average across the Intermountain West, with New Mexico having its warmest October through December period since 1895, and the other states ranking slightly lower, going down to Colorado, which had its fifth warmest October to December period. That same mix of wet and dry on the precipitation side that we saw for the calendar year is existent here as well. Arizona had its ninth driest October to December, while Colorado had its 31st wettest. New Mexico and Utah fell into that normal band, and Wyoming saw its 22nd driest October to December. Now, the January numbers would alter the situation a little bit for the water year, since almost the entire Intermountain West saw negative temperature departures from normal over here on the left, especially in Wyoming, Colorado, and New Mexico. The one exception being up in the northeast corner there of Utah, south of the Wasatch Range, which was just a little bit on the warmer side. Precip on the right was mixed, with Wyoming and eastern Colorado picking up some decent amounts in places, while Utah, western Colorado, Arizona, and New Mexico unfortunately missed out. Okay, so here we have the average mean temperature over the last 120 days, or since about the start of the water year back in October. Gray areas such as in southwest Wyoming, southeast western Colorado, all but central Arizona, and scattered other areas about within a degree of normal, while the yellows and oranges show areas that have been up to 4 degrees above normal, and those red areas scattered throughout Wyoming, northeast Utah, across mid-Arizona, New Mexico, and far south central Arizona too. Up to about 5 degrees above normal. And there's some green areas showing, which are about up to 2 degrees below normal, but they're so scattered as not really being worth mentioning. Okay, also for the last 120 days here, we have precipitation over the region as a percentile, and we've got quite a mix here. Starting with the obvious one, we have Arizona, with all but the northeast part being in the 5th or less percentile for the last 4 months. And then to the opposite side, we have Colorado, excuse me, especially northeastern New Mexico, like say eastern Colorado, there in the 95th or greater percentile. Utah ran from about median in those gray areas down to below median, with the worst areas being in the southwest. And Wyoming was a mix of well below median in the northwest and southeast, and then a diagonal band running kind of between the two of them that was above median. And as would be expected, you get a fairly similar representation when you look at precip over that same period, this time in terms of a percent of normal, so I won't linger on this too long. Okay, snow water equivalent. Map on the left here shows SWE or snow water equivalent in the Intermountain West on this date last year. And on the right, the current SWE. And these are modeled snow water equivalents from the National Weather Service's No Risk or National Operational Hydrologic Remote Sensing Center. Arizona and parts of New Mexico not doing as well as they were last year, but then the northern tier of Wyoming doing a bit better from last year. And that's a bit easier to visualize this on a delta or a change map. So this shows the difference in snow water equivalent from this year compared to last. Obviously, we want to see the green and purple colors, and unfortunately in the 5 states, we're not seeing much of those except for up in Wyoming. Southern Colorado and northern New Mexico on the southern side of the San Juans have not done too well. Too much of that dark red indicating a negative difference from last year of about 2 inches of snow water equivalent or more. Very notable also in Utah, that swath running north-south through the center of the state. All right, instead of the aerial view of this, we got snow water equivalent by each of the basins as a percent of the 1991 to 2020 median. And this compares where we were on this day last year and over here on the left and where we are this year on the right. Right off, you can see that glaring bunch of red down in Arizona and New Mexico with a few little feeders going up into Colorado and Utah. Those basins are all under 50% of median, with most of them being under the 25% mark. Just to their north, there's those 4 basins in an orange color representing snow water equivalent values there that are between 50 and 70% of median. And that whole area from there on down south is obviously doing worse than it was last year. Then most of the remainder of the basins in Utah are all between 70 and 90% of median and are not doing as well as they were last year. Very northern tier of basins in Utah is doing better than the rest of the state. They're generally around or above where they were last year. Over in Colorado, the basins are pretty much not as well as they were last year at this time, especially in the southwest. Northern basins around the median, though, those nice green colors, and you do have that protrusion of the North Platte extending into north central Colorado there that is somewhat better than last year, as is the South Platte that's just to the east of that. And then thanks to some recent snows in the last few days, really, Wyoming basins are doing better than they were a year ago, with the only exception being the Bear down in the southwest, but even that is now up into the median ground. So here's a regional view of the U.S. Drought Monitor. It shows conditions across the 5 states as of last Tuesday, the 28th of January. That's the latest map. Currently, Arizona and Wyoming, as Gretel said, are pretty much tied both in terms of percent of area covered by drought and the percent of area that's in that D3 or extreme drought level or worse. For the category of D3 or worse, Utah and Colorado come in at 0 and just under 1% of the area of the state, respectively, while New Mexico is coming in a little over 5%, and all of that along their southern border. I have to tell you, there's been many times in recent weeks that I've wanted to just label that other rectangular state there south of us and call it Wyoming and hope that changed conditions here. And as you might guess, that doesn't really work that way. Wyoming has improved over the last few months, though. As Gretel was saying, there was a time back in September that we had 100% drought coverage, and that hasn't happened since 2004. So a rare and not welcome occurrence. And just point out the colors here represent the drought category, with the areas of no color being completely free. Yellow areas are D0 or abnormally dry, and I have to quickly point out that they're not technically drought, but it's a borderline condition where an area may be going into or emerging from actual drought conditions. And then there's the 4 levels of drought going from D1 to D4, or moderate, severe, extreme, and exceptional, with the exceptional not showing up anywhere in the 5 states. So that's good, though you can see a bit of it there in the panhandle of Texas. The areas of extreme, though, are large enough and cover far southern New Mexico, western Arizona, a bit of northern Colorado, and then southeastern Wyoming, along with 2 other chunks up there in the northeast and northwest. All right, well, the last map that showed the coverage of drought right now in terms of area. This chart shows a week by week comparison of the percent of the Intermountain West that was in one category of drought or another. This chart starts in 2000, which was the inception of the U.S. Drought Monitor, and then it goes through last week. And at a glance, you can see how this current drought period compares with prior episodes of drought. You can see in terms of area, the 2020, 2021 period there experienced a large area of D4 or exceptional drought that covered more of a region of the Intermountain West than any other point in time in the last 25 years. But keep in mind, this is showing quite a large area of land. So one area that may be completely drought free, there may be other areas that are in the highest category. Currently, just over half of the Intermountain West is in drought, those D1 to D4 categories, while if you throw in that abnormally dry condition, then you have just over 3/4 of the area being impacted. Okay, since 25 years kind of compresses the view quite a bit, and you lose some of that finer details of the variations week by week. This just shows the last 20% of the chart or the last 5 years or so, so you can get a better idea of the fluctuations and see more of the week-to-week changes that you could see in that last chart. So when I talk about similar topics just in Wyoming, I hasten to mention that Wyoming is a pretty large state, so the graph may not represent what you see locally. And the Intermountain West is 5 such large states, so that statement is even more apt in this condition. And because of that, we've developed a tool where a person can choose any spot and see the drought history right at his or her own location. And here, I just clicked on the Four Corners area, just actually right on the intersection of the 4 states, and you get this chart here that is same sort of concept as the previous one, but it shows a different representation of drought levels than it does for the entire area, obviously, because you're looking at just one particular cell on the ground. So I invite you to try that, Earl, on the bottom of the screen there, and just explore the conditions in your area. So here we see how the drought status is in the Intermountain West and how it's changed since the start of the water year back in October. The colors represent the number of categories of change. So going from D0 to D1 would be a 1-class degradation, while if you went from D3 to D1, that would be 2 classes of an improvement. The yellow-orange colors represent degradation, while the greens and blues are improvements, and grays indicate no change in that D0 to D4 level. And there's also some white areas, most notably in Colorado and northeastern New Mexico, but also right smack in the center of Utah pretty much. And those areas were also unchanged, but they had no drought classification to begin with at all. So the gray areas didn't change, but remained either D0 to D4, and the white areas didn't change, but there was no drought class there at all. Arizona has been all degradation with a few small areas that remain the same. The deepest changes there were in the south, where some areas saw 3-class degradation. New Mexico roughly saw improvements in the east and degradations in the west, with areas of no change throughout. And Colorado saw up to 3 classes of improvement, but also had some degradations in the north central areas as well as the southwest, and some of those degradations also being 3 classes. Utah had quite a bit of area with no change, and only one small area there in the center of the state which improved 1 class. And the remainder experienced a 1 or 2 class degradation. Those were mostly in the west and south. And then up here in Wyoming, we saw improvements in the northeast and some small areas of the south central part of the state, but also a fair amount of degradation, with the most dramatic being that 3-class degradation that you see in the southeast down there in Laramie County. All right, jumping over to water supply. This shows the NRCS water supply forecast points, and they're color coded by their 50% exceedance probability. And what that means is there's a 50% chance that the actual experienced stream flow volume will be above the value shown, and a 50% chance that it will be below. So it's the middle of the range forecast values if things remain the same. The actual value that is forecasted is given in terms of a percent of the 1991 to 2020 median volume of flow. So looking down in that area circled in red in Arizona and New Mexico, those red values indicate that the middle of the road forecasted volumes are less than 50% of the median flow. Moving northward into Utah and Colorado, that green circled area there, you can see values in the dots in green and light blue, along with a few yellow, a small handful of the darker blue in Utah. And those green values indicate that the forecast is shooting for within about 10% above or below the median flow, while the light blue and yellow indicate points that could be above and below that range, respectively, by another 20% or so. And then when you get into the northern two-thirds or thereabouts of Wyoming, that area circled in orange, you can see a mix of yellow, red, orange points indicating middle of the line forecast range there, where the points are expected to be about 90% of median or less. All right, a look at current reservoir storage, and this is from the Bureau of Reclamation. This shows the reservoirs in the area with the size of that circle being an indicator of the relative storage capacity of the reservoir. And the color indicates a scale of the current storage in terms of a percent of average. And while we do see some bluer colors indicating above average storage, such as Pueblo, Horsetooth Reservoir, Carter Lake in Colorado, along with Jackson Lake up in Wyoming, we see more of the reservoirs are in that light to dark red color there in the Intermountain West. And unfortunately, the two largest ones in the Southwest, those being Lake Powell there on the Utah-Arizona border and Lake Mead a bit further downstream, those two are both showing that they're at about 34% full. And as far as average, 57% at Powell and 54% of average at Mead. And a particular note on the teacup diagrams there on the bottom of the screen is that lower set of dashed lines there just above the blue, and that indicates the 10th percentile mark. And both Powell and Mead are below those lines and are at the lowest values for this day of the last 30 years. So what are the projections looking like for those two reservoirs? Well, these are 2-year projections, also from the Bureau of Reclamation, and show probable maximum elevation. It's that blue dashed line, along with the probable minimum elevation, which is the red dashed line. And then you have a most probable or most likely elevation there in green. And those green or gray lines actually that you see inside the shaded area, those are the traces of each of the 30 projected study results that go into the makeup of those probable values. And so the most probable elevation line, that green one, it has a little seasonal ebb and flow there, but it's roughly level at Lake Powell and with an even upward slope, if ever so slightly, there at Lake Mead. So what are we looking at the next 7 days for precipitation? This map is actually earlier from yesterday, so while the coverage is about the same now, the magnitude or amounts of forecasted precipitation are a bit higher on this map than the one today, since some of the precipitation on this map has already occurred. One slide I wish I'd been able to throw in here was a photo from our Buffalo Bill Mesonet station up in the northwest part of the state, and it's only at just under about 5,500 feet elevation. And from noon on the 2nd to around 2 or 3 in the afternoon yesterday, we got 19 inches of snow there. So come on, let's have more of it. Currently, Arizona and New Mexico are again missing out on the precipitation. Western Wyoming, north central Utah, the higher elevations of Colorado and Utah could still see another inch or more of liquid, while the lower areas and those lighter and darker green areas expecting under a half inch or less. Going now to the week following that, the 8 to 14 day temperature outlook from the Climate Prediction Center. Temperature here over on the left, great chances for below normal temperatures in the northern half of the Intermountain West. Less chances in the southern half, but still a wide range of below normal temps. This map is also from yesterday, so it's always a moving target. The lesser likelihoods for below normal temperatures were in the south on the map yesterday, one that you see here, and those chances have lessened in the Arizona-New Mexico border area to the point where temperatures there are looking like about normal. For precipitation there on the right side, chances for above normal precipitation in all but southwest New Mexico and much of Arizona, except for that northwest corner or northeast corner. Chances are best in Colorado, but even there, it's only a strong leaning. And that also has changed in the last day with the area of darker green there in Colorado being limited now more to the central part of the state with a slight chance of some below normal precipitation actually having moved into southwestern Arizona, unfortunately. Okay, it shows 1 month outlook for temperature, again on the left, and precipitation on the right. Generally looking at better chances of above normal temperature for the southern half of the Intermountain West, although the signal does not get too strong until you get into New Mexico there. The odds favor below normal temperatures in northeastern Wyoming and even chances for above normal or below for the rest of the region. For precipitation, a slight chance for below normal precip in New Mexico, maybe extending somewhat into southeast Arizona. Northern Utah and western Wyoming have better chances for above normal precipitation, but not an overly strong signal there, except for some small portions. The rest of the region could go either way. Stepping out to 3 months, the February through April time period, we see southern half of New Mexico likely to see above normal temperature, and about the southern 3/4 of the state likely seeing below normal precipitation. On the temperature side, we see the diminishing chances for that above normal temperature there on the left map until we get to about the middle of Utah, and then line diagonaling downward to the southeast through Colorado. Above that, until you get to a line that sort of divides Wyoming through the northwest and southeast corners, you could see above or below or normal, so your best bet is climatology there. Then when we get to that blue area covering the northeastern half of Wyoming, which represents a slight leaning towards below normal temperatures. Just a little on La Nina, you can see the colder waters, those bluer colors there present along the equator, sort of in that long rectangular area. And La Nina conditions are currently present. They're expected to continue through the February to April period, about a 60% confidence level of that. And then there's about a 60% chance that the March to May 3-month period will see a return to neutral conditions. And the effects of this current La Nina are already kind of baked into, if you will, the outlooks that we saw on the previous slides. So what are the outlooks in terms of drought persistence? In the coming month on the left, we can see the same with maybe some slight improvements in northwest Wyoming. Continued drought development is possible in the southern part of the region there in Arizona and New Mexico. Those yellow areas that you see there. And then drought continues, but is expected to improve, I say in the northwestern and Wyoming, and with some areas maybe becoming drought free in the southwest there. Some improvements in northern Utah. Over on the right is the outlook for the next 3 months, and we see similar possibilities of improvement there up in northwest Wyoming, but also the likely continuation of drought development and persistence in the south there, filling out the rest of Arizona and all but northeastern New Mexico, and then extending northward there from the Four Corners area. And Colorado and Utah not seeing too much of a change. So to wrap up here, calendar year 2024, water year 2025, at least through the end of December, saw some above to well above normal temperatures. January temps much below normal in Wyoming, Colorado, eastern New Mexico, and below, to a lesser extent in the remainder of the Intermountain West. January precip was below normal in Utah, Arizona, New Mexico, western Colorado, and was above normal in eastern Colorado and pretty much a mix in Wyoming. Snowpack well below median in Arizona, New Mexico, and southern Utah, about median and above in the northern half of Colorado, and all but a few the northern parts of Wyoming and in far northern Utah. Remainder of the Intermountain West is generally around 70 to 90% of median. The current water supply Shows about median to above median volumes in Utah, Colorado, well below median in Arizona and New Mexico, and then sort of median to below median in Wyoming. Drought development, persistence, likely in the southwest, northwest Wyoming, northwest Utah could see some improvement and even some removal, hopefully. And Colorado looking at staying about the same with some removal in the far northwest. Once we get past the next 2 months, outlook for the next 2 weeks, the outlook for the next 3 months is showing a likelihood of above normal temperatures, below normal precipitation in Arizona and New Mexico. It's starting to sound like a broken record. Slightly better chances for below normal temperatures in the northeastern half of Wyoming, below normal precipitation in the southeastern half, and then Colorado and Utah have better chances for above normal temperatures in the southern portions of those states and below normal precip for all but northwestern Utah. And I think that's it. Yeah, with that, I will close. Contact info is on the slide there, and I will turn it back over to Gretel.
Thank you so much, Tony. That was fantastic. Fantastic presentation and a little bit daunting in terms of drought development, especially for the Southwest. All right. Well, next, I'm excited to introduce Dr. Jeffrey Deems. And Jeff, if you can share your screen, I will hand it on over.
Fantastic. All right. Thank you, Gretel, for the invitation to participate today, and thanks, Tony, for the great overview there and getting everyone focused on the snowpack. I am going to talk today about the airborne snow observatories and the type of measurements and modeling and forecasting that we conduct in order to add to the mix of decision support information regarding our snow water resources in the western U.S. and in the Intermountain West in particular. So let's jump right into it here. If I can advance the screen, there we go. So I'll do a little bit of discussion of the motivation for the Airborne Snow Observatories program and some bit of overview. I'll dive into some of the detail on how it works, all the way from our airborne surveys through to connected runoff forecasting. Show a few highlights and operational impacts that kind of span the gamut of the potential application of the program, and then zoom out to talk about the more programmatic level and program building stuff. So our challenge is that our biggest reservoir, the mountain snowpack, is a pretty complicated beast. The image you can see in the background here is an ASO measured snow depth from April 2019 in central Colorado. This view is looking to the south. That's the town of Crested Butte in the top up there near the words. And you can see the incredibly complicated pattern of snow across the landscape. Some features jump out as what we might expect, with higher depths at higher elevations and lower snow depths down in the valley. And then as you zoom in a bit further, various aspect-driven patterns from the way the storm patterns interact with the terrain and the way that melt and solar radiation in particular influence the snowpack, and then even finer scale patterns due to wind redistribution and avalanching. These patterns, some places tend to repeat year to year. You get a snowdrift in one particular location or a big cornice almost every year, and other things vary seasonally and interannually. It can be a tough thing to keep track of, and the conventional way, and really the backbone of the way we measure our water resource, our snow water resource, is through the SNOWTEL network. In this particular image, there's two stations, one on Mount Crested Butte and one actually in the Crystal River drainage near Schofield Pass. And trying to capture the wide range of variability that can occur in the watershed with just a couple of point measurements really leaves us vulnerable to not being able to detect changes that occur away from those stations. Or to put it another way, that the way that these stations can represent the basin snowpack varies over time from within a particular water year to between water years. Importantly, these stations do measure a continuous time series. So they're measuring continuously, giving us that real-time information about the temporal evolution of the snowpack. What we have to infer with only the station data is what the spatial picture is doing. So that's where we have a bit of a vulnerability in not being able to always detect what the snowpack is up to. Here's an example of exactly that. So looking at the same watershed, this is the East River Basin and the Upper Gunnison River in Colorado. Those same two snowtail sites are marked on the map on the right with the red X circle things. And on the left is the time series average snowpack evolution of those two sites in each of the past 2 years, 2024 and 2023. And I don't have those lines labeled on there. 2024 is the blue line, which is a slightly above average peak or above median peak SWE accumulation at these sites. 2023, much bigger year, well above median accumulation with the green line. ASO flew this basin right around the same dates on each of those years. I've got the 2024 dates labeled on the time series plot, but we were within a couple days in 2023 as well. And the map on the right shows the SWE difference between those flights in each year. So the one showing now is April 3rd, 2024 minus April 1st, 2023. And while the browns, the overall brown color indicates that 2023 did have quite a lot more snow than 2024, reflecting what the snowtail stations show, the spatial pattern of that difference is quite interesting. In the west side of the basin, in the Ruby Range, really large differences with a ton more snow in 2023. In fact, it's a bit off scale on my color ramp here. Well over half a meter of SWE differences in the Ruby Range. Whereas on the east side of the basin, the colors are nearly white, showing not much difference at all. So within the basin, that has importance for the water usage coming out of the eastern draining subbasins of Cement Creek and Brush Creek, and then at the larger basin scale affects the timing and volume of runoff. That's the April flights. Moving into May, we still see this strong east-west pattern, and the snowtail stations are still showing that 2023 had more snow. But the spatial pattern has switched such that there's more snow in 2024 in the eastern part of the basin. So as we move into the melt season, the comparison between years has actually flipped in sign over half of this watershed. So just to illustrate that the accumulation pattern at everywhere from the slope scale all the way up to the basin scale can be very complicated and a difficult thing to track without both the temporal and spatial components. This has a direct impact on our ability to forecast runoff with especially under changing conditions with a warming climate, other impacts on snowmelt like dust on snow, or watershed condition changes like wildfire or beetle kill affecting snow accumulation and melt. The ability to capture the snowpack volume directly influences our ability to forecast the runoff, and that ability to measure the snowpack really varies year to year, or more specifically, the fidelity with which some point measurements can capture the basin scale snowpack variability varies year to year. And we end up with the example here showing big variation in forecast accuracy year to year, such that it demands a wide margin in operational decision making to account for the possibility of big swings either direction. To diagnose this a little bit, we can look at comparing observed snow from the Airborne Snow Observatory to, in this case, the River Forecast Center's water equivalent from their models, which they extrapolate from the SNOTEL network. And the center plots here do that direct comparison of ASO SWE versus RFC SWE. The dots that are right along that diagonal line show really good agreement. Dots that are above show that overestimation in the RFC's water equivalent, and below the line, the opposite, an underestimation. The bottom plot shows 2023, and the majority of those lines or dots are really following that one-to-one line, suggesting that the snowpack was captured accurately by the RFC's techniques in 2023. The upper plot in 2021 shows a lot of overestimation of the snowpack. And on the left, we see the evolution of the RFC forecasts for, in this case, it's the Roaring Fork, but it's emblematic of how things behave statewide in each of these 2 years, with the good beat on the snowpack in 2023 leading to an accurate forecast on April 1st that remained so throughout the melt season. Whereas in 2021, the forecast on April 1st was strongly overestimated, and the forecast was playing catch up through the melt season as the anticipated snow melt didn't come down. I'll note that 2021 is often held out as a case year where we had what appeared to be a relatively normal percent, relatively typical percent of normal snowpack, above 80% statewide, and a much lower than average runoff percentage. And with a lot of the fingers getting pointed at soil moisture as being the culprit there. I think this analysis shows that what's really missing is the snowpack in that case. And that has direct bearing on our ability to proactively get early warning on drought conditions early enough in the season to actually respond effectively. This dependence of forecastability, forecast accuracy on our ability to measure the snowpack really, to me, is encouraging. That provides a pathway forward where we can really tighten up that interannual variability and forecast skill with some additional information. And that's really the motivation behind ASO. We measure snow depth, snow water equivalent, and snow albedo from the air using a combination of LiDAR and spectrometer remote sensing instruments. We combine those with physical modeling of the snowpack and the hydrologic system, with all of it designed for rapid turnaround, high accuracy, and decision support in mind. We started this program at NASA JPL back in 2013, and in 2020 emerged as with a tech transfer effort from NASA as ASO Inc. Basically doing the same thing, but as a smaller shop now. A bit about how we do this, and I'll focus on the accuracy component here because it's critical really to providing that solid foundation on which to forecast our runoff. We begin with a flight pattern that covers ideally the entire watershed in a single flight with a uniform flight pattern. That both allows a maximum area coverage rate for latency purposes, but also gives us that uniform pattern across the entire watershed, which allows us to create a consistent error pattern in our elevation measurements. Our initial processing links the LiDAR and spectrometer data workflows in order to provide better spectrometer retrievals, as well as to better classify the LiDAR point clouds. Then comes the critical step. We're doing an elevation subtraction to get to snow depth. That's a snow-free data set subtracted from a snow-on data set. We snap those two elevation data sets together using the spectrometer detected snow-free areas. That gives us a wide set of effectively ground control points. That is, areas that we know there's no snow, So where we know that we know exactly what the snow depth is there, that's 0, to adjust those data sets to align well together, such that when we subtract them, we get 0 where we can see there is no snow. This does two things. It gives us a 0 bias in our snow depth calculation. It also allows us to quantify the uncertainty in the distribution of errors around that 0 bias. It's typically on the order of a centimeter. And it does so homogenously across the entire data set. So this is really a key accuracy enforcement step that gets us to centimeter scale accuracy at our 3-meter resolution depth grids. We then integrate with snow density, which is produced by the iSnowBal model, which is a physically based mass and energy balance snow model. We use the measured snow depths to constrain the snow state in that model. And then we look at in situ data from SNOWTEL or snow courses or other measurements of depth and water equivalent so that we can make sure that our model densities are unbiased. The product of that 50-meter density with the 50-meter version of our snow depth map gives us that snow water equivalent, which we typically end up at about 5% uncertainty at the basin scale with that SWE volume. A bit more what these data look like. Here's the Blue River in 2019 in April in central Colorado from an April flight and then a May flight later in the season. Obviously, lots of melt out going on at lower elevations. That's fairly easy to detect. Don't even need really remote sensing for that. You can see it at 80 miles an hour on I-70. But what we can't see easily without the ASO mapping is what's going on at those upper elevations. We integrate with the SNOWTEL data. There's 4 stations in this basin to track the melt out over time and to keep the models on track over time. And then we get the snapshots of the full basin snowpack to really help build out the 4 dimensions of snowpack variability. Once we get those maps, we can start looking at we can start distilling the spatial distribution in different ways, depending on what the stakeholder set finds useful. Here we've got both flights by elevation, SWE volume by elevation, and then the top plots there show by elevation and aspect, with the right one being the difference between the 2 flights. We can actually see the strong melt out at lower elevations, of course, but a modest increase in snow water equivalent at the highest elevations on north-facing slopes. So that's really good intel getting late into the melt season for understanding exactly how much snow water is left to come down. These 2 years, 2022 and 2023, the SNOWTEL stations were showing basically the same number in mid-April, but we were detecting about 20% more water equivalent in the basin in 2023. So again, for Denver Water managing Dillon Reservoir there, that's really important, especially for their reservoir operations timing. So we've got our flight and processing that I mentioned. Here's our product suite is depth, density, and SWE, and albedo, and then a couple other ancillary products as well. With the iSnowBal model worked in there, we have a time series of evolution of the snowpack over the entire snow season, constrained by the flight data. That allows us to integrate with other runoff modeling efforts. We've been working with California Department of Water Resources for their B120 forecasts. The Colorado Basin River Forecast Center, as well as the California Nevada Center, have been producing experimental forecasts using their system and ingesting ASO data. And we also have been producing physically based hydrologic runoff ensembles using the WRF Hydro system. And I'll talk about that here for a bit. WRF Hydro is a physically based hydrology model. It involves the snowpack and the land surface and subsurface conditions over time. We're running it at a 1 kilometer resolution, and it's involving a bunch of different snow states as well as other water balance components, and really having the flight data available to constrain the biggest seasonal storage term here is a big advantage towards uh, tightening up that model's performance for the April through July runoff forecasts. Our system and our workflow basically works like this. We have our meteorological forcings that run the daily model analysis of the full water and energy balance. This setup is based on the national water model implementation, so it's deployable and scalable throughout the continental United States. We then bring in the flight data to constrain the water equivalent, which then allows us to initiate a new forecast from that flight date and generate ensemble runoff and inflow forecasts from that date forward, using the past 25 years of observed weather as our ensemble members. This year we've expanded some of the data assimilation techniques as well, and upgraded the system over last year. The ensemble forecast is really kind of the flagship product. Here's showing the open loop and then the ASO data assimilated ensemble forecast for Taylor Park Reservoir in 2023. And you can see that the assimilated forecast has a much tighter spread in the ensemble, in the range of ensemble members, really helping confine the uncertainty to the future weather going from the point of the forecast date. Within the model, in addition to that ESP forecast, there's a whole bunch of other analyses that are possible from water equivalent to soil moisture states. We can compare to other model systems or snow analyses like SNODAS to really help evaluate the current conditions and look at multiple products at the same time. In particular, there's several of these products that are really relevant for drought analysis and forecasts. In particular, the soil moisture analysis, both spatially and aggregated by elevation, as well as evapotranspiration demands and the ensemble forecast for those different components. All this together has a bunch of different decision support applications, either the snow products themselves or by themselves or the runoff forecasts. We've had a wide range of applications west-wide, from reservoir operations to flood management and supporting fish flow timing for fish recovery programs. I want to highlight a couple of different examples here. This one's from California, so not Intermountain West, but I think really an emblematic case study of adaptive management under changing conditions. So in 2022, in the Feather River in Northern California, this is the water supply for the State Water Project. And 60% of this basin has burned at medium or high intensity over the past 6 years. So lots of change going on in this basin. We flew in mid-February, and the SWE volume we came up with was about half of what some other estimates were showing, which wasn't really good news, but better to know that in February than to wait until the water doesn't come past the gauge. So some early warning of lower than anticipated snow accumulation that year. Our 2 flights in March showed that meager snowpack again decreased by half, which was a pretty extreme melt rate for March, even in this basin. And our analysis from the spectrometer showed that it was largely soot deposition from the recently burned forests, lowering the snow albedo and causing much faster melt. So here we've got kind of twofer or a double whammy of reduced snow accumulation from what might be a prototypical climate change impact year, as well as impacts from wildfire and forest condition affecting, in this case, the snow melt in addition to the snow accumulation patterns. So a couple different ways that ASO data can support adaptation under these different conditions. A couple examples from Colorado from the past couple years. The Dolores River, last year, we flew 2 days in April. The first flight in particular was alarming at how little snow was up there, and which really provided some early warning of lower than expected runoff conditions last year. That snow quantification in April really helped us get the WRF hydro forecast on track early. We validated to within 1% with our early April forecast. The River Forecast Center experimental forecast was also brought down substantially by ingest of the ASO data there. So really helping across the board to give the McPhee Reservoir and Dolores Water Conservancy District managers a bit more heads up that they were heading into drought conditions last year. As with the East River, similar graphics here, showing again much lower snowpack in 2024 than in 2023. I think the SNOTELs are doing a good job in this case of giving us a heads up on that, but the SNOTEL network alone is still showing above median conditions in 2024. And there appears to be quite a bit less snow than we would typically expect from those kind of conditions. Moving later in the season, these are two very different dates in 2024 and 2023, late April and late May. But if you look at the spots on the SNOTEL curves, they represent about the same amount of snow on the SNOTEL networks. I think average, the SNOTELs in this case are probably doing a good job of showing us the average conditions, but the distribution is quite different year to year, as highlighted by the colors in the map, which is very important for managing the flow out of the different sub-reservoir or sub-watersheds in the Dolores and appropriating water rights there. I'll quickly go through the Taylor River here in 2024. An interesting case here where both forecasts validated pretty well from April 1st in the single digit range. In this case, our forecast got worse in June. And this was interesting because, and really informs the flight timing. We can see, again, similar maps here, comparing 2024 and 2023. As we move into May, we see that 2023 was quite a lot more snow than in 2024. This was largely due to snowfall in May. And we had been melting off a bit quickly in the WRF hydro model in 2024. And therefore, when we assimilated the May 20 flight, we actually put snow back into the basin that we had already run off. So that decreased the forecast accuracy. Good lessons learned here, both in terms of our assimilation techniques, which we're refining this year, as well as for flight timing relative to spring snowstorms. It's really advantageous to try to be able to capture those. So some good lessons there. So big picture going forward, we really see the ASO capability as being a part of our integrated monitoring and forecasting system, building on the SNOTEL and snow course measurements that remain a critical element to this, and enabling a broader suite of forecasting applications from current operational ones to forecast systems that are based on more physically descriptive parameters, really helping us to build out the full 4-dimensional picture of the snowpack. Going forward this year, we've got 86 surveys planned in 34 basins west-wide, a large fraction of those in the Intermountain West. You can see kind of the timing of those in these tables. We've already started flying in California, in the Feather, the Kings, and the Kaweah River out there, and we're expecting or planning on starting up the Colorado and Utah programs here in the middle of next month. So to summarize, relying only on station data, I think presents some clear drought detection and early warning vulnerabilities. Adding a couple more dimensions of the snowpack using ASO type observations can really help accurately capture the state of our biggest seasonal water reservoir, and also enable a more physics-aware runoff forecasting paradigm that will allow response to changing conditions in our watershed and our climate. Please reach out to me with any questions and check out, get some more information on ASO at our website at airbornesnowobservatories.com, or also the QR code there at the bottom. Thanks very much.
Thank you so much, Jeff. Wow, it's such an incredible asset to moving forward with drought early warning and water management. For anyone who is interested in sharing these presentations and this webinar, they are recorded and they are available on our YouTube channel, which you can access at that URL or using that QR code. And our next webinar will be on April 1st. And please take a look for that, either by signing up for those webinars through this QR code or going to that URL on drought.gov. We welcome your feedback and look forward to hearing from you. So thanks again so much to everyone who joined, and very special thanks to both Tony and Jeff for their presentations. Thank you. Have a great day.